Okay. So in the last lecture, we talked about Fourier series. So let's just take a small recap, and then we'll start going further as well. We talked about Fourier series, how a mathematician named J. Fourier from France was talking about how we can express a periodic signal as a sum of various components of harmonic components. Can you guys see the screen clearly, or is it a little too blurred? You would like it to be zoomed more? Yes? Okay, let's do that. Okay. Is this better? But somehow still not clear, right? Okay, I don't know why. Okay, once I get into focus, how do I focus? Okay, this is... Okay, this is better, right? Okay, so let's get started then. So we talked about Fourier series, where we were talking about how a signal, if it is periodic, can be expressed as a set of harmonic components with a fundamental period, which is 2 pi over t. And as you go further into higher frequencies, you get higher and higher modes. So we saw how the fundamental frequency is this one, and then we have the higher frequencies, which are also periodic with t, but also actually have a much smaller fundamental period. And our whole idea was to express any kind of a periodic signal which is not harmonic in terms of harmonic components, because we know how to work with harmonic components. So if you're able to reduce a periodic signal into a set of harmonic components, then we can go ahead and find the acceleration and the velocities by simply differentiating the time signal. Okay, so in order to determine those coefficients, what we did was we used the orthogonality principle, or the property that sine of cosine omega t and multiplied by sine of omega nt will be 0 for all m not equal to n, and will be t by 2 for m equal to n. Similarly for the cosine terms as well, and all cross terms, cross multiplication terms are always 0. So through this, we were able to get an expression for these coefficients an, am, and bm in our Fourier series by multiplying the signal by the cos of omega mt and integrating it so that all the rest of the terms in the series go to 0 on the right-hand side, and all you're left with is the coefficient am. And we were able to get the coefficients as these. These were the real Fourier series coefficients. Then we talked about how we can convert, using our Euler's formula, convert cosine of omega t and sine of omega t into exponential form, and putting that into our Fourier series expression, so substituting for cosine of omega mt and sine of omega mt using the Euler's expansions, we were able to get an expression for the complex Fourier series. Or in other words, we were able to get an expression like this, where x of t could be now expressed as the infinite summation, where Cm is a complex number given by our real Fourier series coefficients like this. And then finally, we talked a little bit about how to get the complex Fourier transform coefficients, and the process was similar because we already knew am and bn. We were able to substitute their expressions into it and use the Euler's expansion theorem in order to come up with the complex Fourier series coefficients. Finally, we talked about how a function can be expressed as a sum of an even and odd function, and then how this can help us with some of the calculations of these integrals. It can help us simplifying some of these integrals, because we know that the even part of the signal times sine of omega t when integrated from minus t by 2 to t by 2 will always be 0. Similarly, the odd part multiplied by cosine of omega mt will always be 0 when integrated. Finally, we talked a little bit about Fourier spectra, and then we moved into MATLAB, where we saw how the Fourier expansion actually gives us the signal. We recovered a particular problem in the book, and we tried to look at how the Fourier expansion works in terms of capturing the signal more accurately. So far, any questions? No. Okay. Excellent. Let's proceed forward. So today we'll try to quickly wrap up chapter 1 and go into chapter 2 of the book. So it's lecture 3. So today we'll primarily be focusing on free vibrations. But before we go into that, I want to go over a certain vibration terminologies. So the first thing we'll try to talk about is the peak value. So what a peak value of a signal means is the maximum value of a signal in the entire time series. So it's the maximum value. So if we have, say, a signal, let's say, which looks like this. Okay, so I'll say this is our x of t versus t. And then this point here will be our x max. And that is the peak value within the time series. The second quantity we define is average value. And we denote it by a bar over the x as x bar. And x bar is given as limit t tends to infinity 1 over t integral 0 to t x of t dt. So it's nothing but a simple time average of the signal. So we take all the points in the time and then sum them up and divide by the total time. And in terms of a continuous function, the process is synonymous to an integration. But if you had a discrete time signal, then you would essentially be summing it up over discrete small intervals. So average value of a sine wave over one period is 0. And everybody follows why it is 0? Because in one time cycle, it goes up and down. So when you integrate this process x of t from 0 to t, this area is equal to this area. But they're opposite in sign. So when you add them two up together, you get nothing but 0. However, if we take a look at average value, over a half cycle, then our x bar is given by, so we are now going to sum it over t by 2. So 1 over t by 2 integral 0 to t by 2 a times sine of 2 pi over t times t. Yeah. And you can evaluate this integral and it will come out to be 2a over pi. Or approximately that's 0.637 times a. So the average value of a sine harmonic signal over a half cycle is not 0, but it is some constant value times the amplitude. Right. Now the third thing we'll talk about is mean square value. Sorry. Yeah. Right, mean square value. And this mean square value is generally associated with energy. So it's kind of representative of how much energy there is in the system. Make this a little straight so that it's easier. Okay. And this one is nothing but an average value of square of the signal. So it's x square bar, or in other words, limit t tends to infinity 1 over t. So it's an average 0 to t, but instead of x of t, we have x square of t dt. So again, if we consider x is equal to a sine omega t, or where omega is 2 pi over t times t, then x square bar over one cycle is 1 over t integral 0 to t a square sine square omega t dt. In other words, this can be written as a square over 2t into integral 0 to t 1 minus cosine 2 omega t. So we have here used a trigonometric formula for converting sine square omega t into a cosine of 2 omega t. So the formula we used is 2 times sine square theta is equal to 1 minus cos 2 theta. So this is the relation we have used. Alright, so integrating this further, we find that this value is nothing but a square over 2. And the fourth thing which we are looking to look at is called the root mean square value. Or in other terms, it is also known as RMS value in a simplification. So x RMS is nothing but square root of x square r. So we found the mean square value. We just take a square root of it and we get root mean square value. So in terms of if x is a sine omega t, then x RMS is nothing but square root of a square over 2, as we found before, or a over square root 2. That's around roughly 0.707 a. And the last thing we're going to define is called a decibel. Decibel is a unit defining the ratio of power between two signals. So it's nothing but a ratio of power between two signals. And it's denoted as dB. Okay, I need a little more space here. Just a second. Okay, let's go. So that is defined as 10 times logarithm to the base 10 of power in signal 1 versus power in signal 2. And we know that power is nothing but energy, is a relationship for energy between the two signals. And energy, as we saw, was related to the mean square value, or in other terms, the square of the amplitude. So in certain sense, you can say that this is nothing but log 10 of x1 over x2, so the signal itself squared. And is a fair representation of the decibel level, which can also be written as 20 times log 10 x1 over x2. Although we really will not be using decibel very much in our application to the marine sciences cases, but this is a unit which you need to be familiar with because sometimes in the electrical engineering and other areas, people like to talk in terms of decibels. And it's nothing but at the end of the day just a ratio between the power of two signals. Okay, so far any questions? All right. Okay, so now let's begin with what we actually want to start today, the free vibration. So free vibration refers to the vibration in the absence of any external excitation. Refers to the vibration So that means that when we are considering a free vibration problem, there is no external forcing. And similarly, we also assume for the present there is no external damping. And what that means is we do not have anything which is providing energy to the system, neither we have anything taking away energy from the system. So the system is contained in itself and is a conservative system. So we'll talk about what a conservative system is in a little bit. So let's take a look at the, the most simple free vibration problem. So we have a mass M suspended from a spring, as shown here. And so let's say the original unstretched length of the spring was up to this level. So this difference you see here is the static extension. So let's define the terms we have mentioned in the diagram. So K is the spring constant. M is the mass. And delta is the static extension. So we know that in the static case, if we draw a free body diagram for the mass, there are only two forces acting on it. The gravity force, which is downward, and then you have the spring force, which is K times delta. And since the body is in equilibrium, we know that mg must equals K times delta. Or this, in other words, gives us an expression for the static extension, which is weight of the mass we are considering divided by the spring constant. So now let us consider that from this static equilibrium position, we displace the mass further down. So we're going to define a point O. So let O denote the center of the mass in static equilibrium. And let and X denote the displacement of the mass from O and is defined positive for downward direction. So all we have done here is that we assume that O is the center of the mass in the static equilibrium position, and then we are displacing the mass further down by X. So now let's construct the free body diagram. for this case. So we have the downward force acting mg, and again we have the external spring force acting, which is k times delta plus x. So why is it delta plus x? It already had a static extension, delta. And then in addition, we are adding an additional displacement x. So total spring force is going to be k times delta plus x. And of course, the body just doesn't have a displacement. It also has a velocity and an acceleration, which we all assume to be positive in the downward direction at the present point. It doesn't matter if you took displacement to be positive upward, then you would have considered the velocity and acceleration also positive upward, and it would have still resulted in the same answer. But then you would have had k times delta minus x here. But you can verify yourself later on that we would have ended up with the same relationship as we're going to derive now. So now we apply Newton's second law. And that's nothing but sum of external forces on the body must equals mass times acceleration. Okay, so all the external forces are nothing but the gravity and the spring force. So mx double dot is equal to, downward is positive, so mg is positive, and k times delta plus x is in the negative direction. So minus k times delta plus x. But we already know that mg is equal to k delta. So therefore these two terms cancel out each other, and we are left with minus kx. So combining the two together, bringing all of them into the left-hand side, we can write it as mx double dot plus kx is equal to 0. So because of our choice of static equilibrium position as the origin point, we see that we have eliminated the force due to gravity from our equation of motion. So our equation of motion doesn't have any gravity term in it, so all the static forces are gone. And this is because we chose the origin point O. In this diagram, we chose origin point O at the static equilibrium position. If we had chosen the origin point at some other place, then you can verify yourself that your right-hand side would not be 0, but indeed would have some of the static terms included here. So going back here, so it kind of gives you an idea that you would always want to construct an equation of motion considering the origin point at the static equilibrium. And that does make sense because when you're considering dynamic forces, we are considering a mean oscillation about the static position. So it makes sense static position to be taken as the origin point and deriving your equations of motion. We can also write this equation as x double dot plus k over n times x is equal to 0. So if we now define, let's define omega n square as k over m. And that makes this relationship x double dot plus omega n square x is equal to 0. And does this equation seem familiar to you guys? Yes. Where did we see it? Yes, you're right. So when we saw for harmonic motion, we wanted to find what is the governing differential equation. We found that it was an equation very similar to this. So, from previous lectures, we know that this equation is the governing equation for harmonic motion. So although we know that harmonic motion is the solution for this differential equation, let's try to officially derive it here so that we understand it's not just a trial and error thing, but rather we can actually derive that it's an harmonic solution. So let's derive it here. So whenever we have a linear differential equation, one of the candidate solutions for this sort of a problem is always x of t is equal to e to the power some exponential factor times t. And we can see that if we substitute this solution into our differential equation, before we do that, let's derive the expression for x dot of t. That's nothing but s into e to the power st. S double dot of t is second derivative, which is again s square e to the power st. Okay. So, substituting into the governing equation, we get s square e to the power st plus omega n square e to the power st is equal to 0. So that implies s square plus omega n square times e to the power st is equal to 0. Now we know that e to the power st is not 0. So not equal to 0. So therefore, this implies the rest of the term must be equal to 0. So s squared plus omega n squared equal to 0. Or this implies s is equal to plus minus I omega n. So there are two possible solutions, e to the power plus I omega nt and e to the power minus I omega nt. So any general solution for the governing equation. is given by x of t is equal to c1 e to the power plus I omega n t, so the first solution, plus some constant times the second solution. Now we also know that e to the power I omega n t and e to the power minus I omega n t can be written in terms of sine and cosine terms using the Euler's formula. So another possible way of writing the solution could be a times cos of omega n t plus b times sine of omega n t. And it is easy to show that these two forms are interchangeably exactly the same. So one can be derived from the other. Although we're not going to do that here, I'll leave it as an exercise in case you want to give a try to it yourself. Chandran, I think I lost the video again. Do you think we can get it back? Okay, let's continue in the meanwhile. So, yes, now I can see. Thank you. So, the generalized solution, we found that can be expressed as a times cosine of omega nt plus b times sine of omega nt. Okay, so let's see. But how do we evaluate what are this a and b? So, okay, so far so good. We know that x of t can be written as these terms, but in order to get the value of a and b, how do I get them? So there are two unknowns in this equation, and for that we need two initial conditions. So the unknowns and since we had originally a second order differential equation, does everybody understand what I mean when I say second order differential equation? So what is a second order differential equation? Anyone can answer. When all of you talk, I can't hear you literally anything. A little louder, please. So what is a second order? Why is this equation a second order differential equation? Yes, it has a second derivative term. That's why it's a second order differential equation. If it only involved first derivative terms, then that would be a first order differential equation. So since we have a second order differential equation, we definitely need two initial conditions. As we are solving a second order differential equation, we need two initial conditions. And usually these two initial conditions are given in terms of what is the initial velocity or initial displacement at time t equal to 0. So it's quite common to give specify them in terms of what the value of the displacement and velocity is at when time t is 0. However, technically speaking, you could specify them at any point t, and those could be as given as the initial condition as well. But it's most common for it to be given at time t equal to 0 because you want to know how the solution evolves once you specify an initial condition. So let's say that we are given the original displacement, which is given as, say, x0. And let's say our initial velocity is given as v0. So how do we get the solve the differential equation? So we substitute t equal to 0 in the above expression into this one, and then equate it to x0. And similarly, we do the same for the second equation as well. So we take a derivative of this equation and then substitute time t equal to 0 and equate it to v0. And that will give us two equations. So let's take a look at what those two equations are. So in the first case, we have x0 is equal to a of cosine omega n0 plus b of sine omega n0. So that's nothing but a, because cos of 0 is 1, sine of 0 is 0. So that directly gives us a is equal to x0. Now let's consider the expression for velocity. So x dot of t, let's first calculate that. So that is nothing but minus omega n a into sine of omega n t plus b omega n into cos of omega n t. So now substitute t equal to 0 and equate this thing to v0. So we have v0 is equal to minus omega n a sine of omega n0 plus b omega n cos of omega n0. So v0 is omega n times b. What this implies, b is v0 by omega n. So we already got our expressions for a. Now we got our expression for b. And putting these expressions back, we can write x of t as x0 cos of omega nt plus v0 by omega n sine of omega nt. So given the initial conditions, the velocity and displacement at time t equal to 0, we can calculate what the exact solution will look like. Okay, so far so good. Does everybody follow me here? Okay, excellent. And we saw that we defined omega n as square root of k by m, and we call omega n as the natural frequency. So omega n is called the natural frequency. And we define something called natural period of the system, which let's call it Tn. That's nothing but 2 pi over omega n. So the subscript n stands for natural, so omega n means omega natural frequency. So this is nothing but 2 pi square root of m by k. All right. Any questions so far? Sorry, what? Sorry, can you speak again? slowly? Okay, you want to copy it down, okay. All right. Let's go ahead and take a look at a couple of examples. So let's take the first example as a simple one. So let's consider a cantilever beam and assume that the beam itself does not have any weight. It's I know a little counterintuitive given that my drawing shows that it has a big shape and a mass, but let's assume that the beam is weightless and we put a mass m at the end of it, and we define the deflection x from the static equilibrium position after the mass has been placed. So we want to now find out what is the natural frequency of this system. From our strength of materials, we know that when some load P, so let's say from when a concentrated load P is applied to a cantilever beam, the deflection is given by PL cubed by 3EI, where E is the Young's modulus and I is the second moment of area of cross section, and L is the length of the beam. So from this we can see that actually this cantilever beam indeed does behave like a spring whose spring constant is given by 3 times EI over L cubed. So if I apply a load P at the end of the beam, it results in a deflection of this much. So that means if I deflect the beam by X, then it will result in a restoring force of P. So it's, in essence, the reverse is essentially, in essence, looks like a spring. And the spring constant for that system is nothing but 3EI over L cubed. So the natural frequency of the system is nothing but square root K over M. So in this we have K as 3EI over L cube. So our natural frequency is nothing but square root of 3EI by ML cube. Now let's take a little more complicated example, and then hopefully I don't think I'll have more time to go further. Okay. So a beam is simply supported at this point and is attached to two springs. So both spring constants are K, and so this distance is A and this distance is B. Let's say the total length is L. And let's assume the center of the beam is here, and the simple support is at a distance C from the center of the beam. And this is at this point be called G, the center of the beam or the center of gravity. And let's assume that the beam is horizontal in static equilibrium. Yes. C is the distance between the simple support point to the center of the beam. And let's assume that the original forces in the spring are P1 and P2. And both are acting upward. So the static forces are acting upward. But we will see that since we are again basing our assumptions that we are going to start from the static equilibrium point as the origin point, the static forces will not result into our final equation of motion for the dynamics. Okay, so what is happening here is now we are going to take this beam and slightly bend it. Not bend it, deflect it by certain angle theta. And let it go. And when you let it go, it will start to oscillate, and we want to now calculate the natural frequency of this system. Okay, I think you guys should attempt this problem for a little while. Okay, I do think I have one more thing to give you before you can attempt. Let the simple support point be called O. So the moment of inertia, so mass moment of inertia, about O, let's say, is called J. So now I want you to calculate the natural frequency of the system. All right. How many of you have got it? Did anyone have the answer yet? Okay, so, all right, be working. In the meantime, I'll also start working on the problem, and then by the time I'm done, hopefully all of you should be done as well. So let's take a look at the beam and what are the forces acting on it. So in the deflected case, you have some reaction force acting on the simple support point. Let's only consider for a minute the static case. So let's take this static case. So we have the force here acting P1 and here acting P2, and then we have from the center of the mass acting M times G. And again, this distance is A, this distance is B, and this distance is C. So since all of our rotations are happening about O, so let's consider the sum of the moments about O. And we know that in the static case, this must be equal to 0. So that means mg times the distance c. So let's consider the anti-clockwise direction. As positive. So we have mg times c, which is anti-clockwise, results in an anti-clockwise moment. Then we have P1 times A, P1 times A. So we are considering moments about this point, O, minus P2 times B. Why minus? Because this has a clockwise direction. This will result in a clockwise moment. Okay, so this must be 0. Yes. Sorry, come again. Oh, okay. Okay, yeah, you're right. So I think I messed it up. It should be clockwise positive is what I'm considering. Actually, it doesn't matter which side you take, because all you will end up with is a negative of the original equation. But yeah, let's make it right. So clockwise direction as positive, then yes. mg times c plus p1 times a minus p2 times b becomes 0. So now let's consider the dynamic case. So in the dynamic case, again, we have the same forces which we had, P1, P2. We have the reaction R, and then mg. But now we also have additional forces. Because we displaced the beam by angle theta here, so the spring force will increase by whatever deflection is here. And that deflection is nothing but B times theta. So B times theta times K will be the additional dynamic force you'll see at the corner here. K times B times theta. And on the right side, on the left side, you'll also see another spring force, but this will be in the opposite direction. Okay. Yes. And this one will be k times a times theta. All right. Does everybody follow me? Okay. So now let's consider the dynamic equilibrium. So that is nothing but sum of the moments about the point O is your moment of inertia times the angular velocity, angular acceleration. So it's a counterpart of our Newton's second law for translational systems. So in terms of a rotational system, that's how it's going to go. So again, considering that the clockwise direction is positive, just as before, we have mgc plus p1 times a minus p2 times b. But now, in addition, we have some additional forces. We have minus kb theta times b. And again, we have another force, ka theta times a. But then again, this one is also in the negative direction because it has an anti-clockwise sense. So minus ka theta times a. That is equal to j times theta double dot. But I'll give you a minute to just take this down quickly. So now in this part, we know that the term within this bracket goes to 0. So all we are left with becomes j times theta double dot plus k times a square plus b square times theta is equal to 0. Or in other words, we can rewrite it as theta double dot plus k times a square plus b square by j times theta equal to 0. So what is the natural frequency now? It's pretty easy, right? So the natural frequency of the system is nothing but the square root of this quantity k times a square plus b square by j. Alright, so that is all we'll have for today's class. So we today talked about how we can apply Newton's laws of motion and derive the equations of motion, and based on that calculate the natural frequency of the system. Tomorrow, on Thursday, we're going to talk about the energy method, a different approach to derive the same equations of motion, and probably look at a couple of more examples. And we'll also see how the two methods essentially give us the same answer. So it's kind of a check that from both methods you should get the same answer. All right. Thank you very much. See you again on Thursday.